Today's discussion is titled Lessons Learned: Why Qualification and Design Matter when Building Batteries and Battery Packs and Battery Systems. We're very fortunate to have with us today a special guest, Erika Guerrero of Electric Goddess. Erika is an accomplished entrepreneur and leader in the battery industry, founding Electric Goddess to provide specialized consulting services and operate a dedicated test facility for battery innovations across automotive, micromobility, energy storage systems, aerospace, and space applications. Erika leads Electric Goddess with a focus on cultivating sustainable technology for the circularity of the battery industry and paradigm innovation through technology development. Yeah, Electric Goddess it's a really cool organization. She and her partner Luke know an awful lot about everything that can go right with batteries and everything that can go wrong with batteries. There's Luke. Hey, Luke. And
Hello.
so we're really excited for today's discussion. Of course, joining me as always is my co-founder and Voltaic CEO, Tal Sholklapper. Tal is my co-founder at Voltaic, who's got a couple decades of experience in batteries and electrochemical devices and things like that, and has been running Voltaic along with me for the last 13 years. I am now going to turn it over to our special guest, Erika Guerrero, who's going to present some introductory material that will guide the rest of the discussion for the day. And again, please feel free to interact through the chat window, but we'll start taking questions after Erika's finished presenting her material. So without further ado, Erika, please take it away.
Thank you so much, Eli. And Eli and Tal, it is so rare to find two people so dedicated to help the industry. And the product that you've created is just truly remarkable, especially someone who works in R&D, to be able to actually see and analyze data, because things get stuck in silos all the time, even at my facility. And so pulling it all together is truly incredible. So thank you for your work.
Absolutely.
So I have just a quick presentation here to just give some overview of why qualification and design matters. I'm specifically focusing on cell design right now, but because cells are the first part of a great battery. And Luke and I have been in batteries for a while. Luke, way more than me, has over 19 years, millions of batteries out in the world. I'm truly lucky to receive a lot of his knowledge every day, and as well as operate two companies, both Electric Goddess and a battery recycling company called Revivis. So there are risks and defects commonly associated with lower quality cells. We like to say there's 1,000 ways for a jelly roll to die. And this is just because cell manufacturing in general is just a series of super hard battles won at a time. So a good battery requires a good cell, but a good cell doesn't automatically mean a good battery, if that makes sense. And as Eli was saying, if there's any questions about this, I'm really going to glaze over some cell defects overviews. Like really, there's a lot of defects that happen at the edges of the cell. If we were going to say where a majority of the cell defects happen, that's usually where it is. There's separator misposition, electrode overhang mismatch, burrs on the electrode foils. Like as soon as you get a brand new razor that's just cutting all of your stuff, like slitting blade, it is just dulling every time. And so that's just one example of being able to get over. And there's coating defects, impurities, and you can see slurries, solvents, electrolyte, metal foils, equipment. I do see some cells that also still use PET tape, but there's a lot of degradation around that. And then pinhole defects. And I separated out just a few high level, like cylindrical, prismatic, pouch specific. Every battery, I hate to say it's almost like a snowflake, but every battery is different. And so you have to figure out how to overcome all the ways that it could go wrong. So cylindricals.
Erika,
yeah.
I'm sorry to interrupt. We're not seeing your slides in presentation mode. I don't know if you intend them to be in presentation mode, but we still see, there we are. Yeah, so we didn't see the last two slides, if that matters. You're welcome to flip back through them or whatever. But yeah, that much better.
Just some fun. Thank you. There are some fun videos or photos here. This prismatic here was a brand new prismatic and just right on our test fixture, puffed right away, which means that like our intake of like checking OCV and just like making sure the cell was healthy didn't work because it just immediately started puffing and gassing. This is a cool CT scan. You probably can't see it, but there's a little white speck in there, which means there's a little bit of metal. This is a new pouch cell that just has bubbles, because pouch cells, if you just handle them or if somebody's packing them to send them to you, they can just be like cracking the cell right away. And then you can see right here in this jelly roll, there's just a lot of separator and foils touching as well. Thanks, Eli, for telling me this. I'll just have to leave it in this format if it's not changing. So with cylindrical specific, when you're like winding a jelly roll, you like the most inner parts of the cell are the most bent radius. And so there's a lot of basically cracking that could happen. So the winding process is relying on binder retaining adhesion to the current collector foil. And then with prismatic, there's edge folding. So they essentially have, some prismatics are a big jelly roll and then they shove it into a square container, or there's Z-fold electrode. And this is where I was talking about the slitting blades and the die cut stamps that causes burrs. And then the pouch specific, there's a little vacuum that comes down to stack the different layers within the cells. And that could, when Z-folding, and that could also cause cracking. And so one thing, if you have questions as well, is that Luke helped in China, a big company, actually get their manufacturing ramped up for cell defects. So he's personally gone through these battles as well. This is one of the most intense cell defects that we've seen on the right here. But really what the risks of cell defects are, you have like puff cells, there's an increase in impedance, self-discharge, decayed lifespan, shorting. And then when you start getting into like really bad things, you have electrolyte leakage, HF, other toxic gases that are released. There's internal pressure that can build up within the cell through excess gas production. And really, it ends in a few ways, right? If there are cell defects, you're either warranty replacement, which is actually the least expensive to do, or you have like thermal runaway plasma in the products and you are buying structures, which is the most horrible outcome to have as well. Non-usable batteries, especially spending a lot of time in recycling lately, they're basically stored in different facilities. So even if these are damaged, defective, or recalled, there's sorting facilities that are holding these batteries prior to, and there is a huge fire risk even before recycling. So a good cell and battery is one that you never have to think about once it's left the factory. And humans have not made a perfectly defect-free cell. And this is showing how fussy we are, especially with like atomic layer deposition and really talking about what does perfect mean in crystal structures. And when you're screening quality defects, there's two types of cell analysis that we normally use. One is destructive, and this can be like accelerated rate calorimetry, checking the separator overhang, doing electrical safety tests. Luke likes a cryogenic temperature hypot to failure, and then also testing the pinhole defects. And then non-destructive screening tests can be like open circuit voltage over time, CT scans. You can see right here, this is one of our favorite things we've done, is Luke created a little vessel that's full of argon. So we were able to take cell jelly rolls out of our glove box right over to the microscope and get some pretty great images without the degradation of atmosphere. And signatures in electrical test data support defect detection. So there's cell validation. There's two different types of quality control when it comes to cells. One is like, how do you pick the cell? Like a major question a repeated question I've been getting lately is, company XYZ is using this cell, like, why can't I just use it and trust that their data was enough to make that decision? That personally makes me very uncomfortable. One, because there's so many different factors that could go into that, depending on what the cell manufacturer, like the grade that they're giving you, the process that they're giving. There is always a reason to invest in testing to not lead to those defect risks that we talked about. You can do things like CT scans, you can do mechanical teardowns, you can use application-specific electrical testing profiles, you can stress test them. All of this data is gathered, cyclic endurance, degradation rates, again, arc, and it's truly important to establish between lots and intra-lots. So if you are receiving cells, you need to just make sure that you are doing some sort of quality test. And it's based on the problem statement of your application, of course, on the level that you need to go to. But even between lots, I've seen a lot of variations in defects as well. So quality control, There is the double pulse method of OCV and impedance. That's something that Luke can talk a lot more in depth about. Physical property screening, and just randomly select different samples from each lot and make sure you're electrically cycling them and tracking that over time. And safety testing is always something that we recommend. So there is specialty analytics software to use this data to detect quality defects and anomalies, but really just like Voltaic. So it really is the first step. It's knowing what to test and understanding those defects that could happen.
Establishing good baselines.
Yeah.
The signature of a defect.
I don't know if you could hear Luke. So establishing good baselines and then going from there. And as you scale up, you're able to just watch that over time. So that was like my intro there. If that works, I can stop sharing.
That was great.
Any of the
Thank you.
defects that we can speak in depth on as well. So if you have folks experiencing a particular type of phenomena, we're happy to elaborate on that.
Sure thing. Yeah, that's great. We'll continue to crowdsource in the Q&A. I think I'll start in with some questions related to the discussion topics for today. So the first is the risks and common defects associated with lower quality cells. So Erika, you just ran through a million different things that can go wrong with a battery. And of course, there are a million and many more. But when we're talking about low quality cells, so there's of course the temptation with all the stories about overcapacity production in the industry and costs plummeting, but at the same time, the tier one suppliers, a lot of their supply is already bought up, so folks are going to the lower tier twos and tier threes, less known. What kind of defects, if you could characterize, are more common among the cheaper cells of lower or variable quality when you get outside? Not that the tier ones are perfect, but once you get outside into the tier two and tier three suppliers, you're going to be tempted because you see some really cheap batteries in Alibaba. What are the things that are most likely to go wrong with those lower tier, lower price cells?
Yeah, we've had some great quality for lower price cells, by the way. That was like super surprising.
Price and quality don't necessarily track directly. However, I totally understand what you're saying. And as cell makers get asked to reduce dollar per watt hour, they have to pull that from somewhere. And for example, there's never been perfectly pure electrolyte. There's different levels of stacking your nines in purity and ionic contaminants. And one of the ways you can save cost in a cell is by running less pure materials. The other thing I wanted to mention is when people are buying from Alibaba, or we're talking about low quality cells here, if you haven't worked out a buying agreement for binning the cells you get sent, you're being sent the cells that didn't meet any other customer's binning standard.
So what are the risks of that, like receiving?
The extreme risk of it, we've had cells that passed all the OEM QC information and then blew up in the test chamber on the first charge cycle with large prismatics. And this was due to an edge overhang short problem. And this is one of the difficulties with edge burrs, is that they can be in a condition where they'll pass QC because they're not shorting at that moment, but even a small amount of thermal expansion coefficient shifting and Thiation electrode expansion shifting can cause that to shift enough to make contact and develop a short. So mechanical effects like separator positioning, foil edge positioning, it's critical that your anode has overhang over your cathode always in your jelly roll, not just that your plastic film is overhanging, but if you have cathode and anode that are at a similar height, this cell will fail, and it will fail at that region that is overlithiated due to the cathode proximity.
So if you're buying lower quality cells, you have even more reason to do hardcore due diligence.
If you think your business plan works out to use a lower quality cell, then it means maybe that will save you money long term, but it means you're going to need to spend more money initially, and you're going to want to spend more money on your screening systems as well, including software like you guys offer. If you had in a perfect world with a perfect cell maker that never made problems, a whole lot of these things we could just ignore and build batteries. But in fact, that cell maker's never existed yet.
Indeed.
So, there's ones getting very close, of course. So it's like your level of paranoia, right?
Yep.
Yeah.
And I
Paul,
think
did you have a comment? Yeah.
just continuing on this thread, I think just checking those cells up front is really key. And oftentimes, even if you're getting sent those batches to check, those are the binned and curated cells that you're getting to qualify. And so sampling over time is really important. We had a customer that did their qualification and then 6 months later realized they were getting a whole bunch of warranty returns. And when they tried to requalify the cells, realized they were different. And especially as people are cutting costs to like, hey, you negotiated a great deal, you drove down the costs. Sometimes that's coming from a little bit of that overhang disappearing. And I just remember some blatant cases. Eric Darcy at Unrel and NASA just has some nice scans of batteries, and you could actually see the total height of jelly roll is actually decreased. They actually used a shorter battery material like that went into the cells. You really just have to stay on top of this, build good supply agreements, and build trust with the suppliers you're using.
Indeed. Yeah, I wanted to go ahead, please.
We've seen a situation where all the samples that we got, we screened and validated, and the quality was exceptionally good. And it turned out that all the samples we'd been sent had been made on their Korean line. And I'm not going to mention any brands, but in volume production, they used their Chinese line, and it wasn't even the same materials in the cell. Not only was it a difference in winding quality, but it was different materials, even though the cell's external heat shrink says the exact same thing printed on it from the ones we validated. So validate what you get for production quantity. Like Tal was mentioning, the samples you get are often binned, premium cherry-picked samples to bin. So you must validate what you receive in production quantity.
And the story I think of is actually a client that had a great relationship for, I would even say, 7 to 10 years. And all of a sudden they were renegotiating and they sent us some cells that were like, what is this flaky material on it? We're like, that's so weird. We don't know what it is. And through our research, there was fish scales. Like there was like somebody's lunch that was just like on these cells.
Yeah, we were wondering what these little circular round pieces were, and it turns out fish scales were all over the cells.
So it's something to be vigilant about, like for the entire time that you're manufacturing batteries.
That was after many years of sending high quality product. This is one of the things where when people negotiate for lower pricing with their cell maker, and every year they beat them up for another 10% off the price of their cell, you don't know what tier that 10% is costing you or what quality steps they're skipping each time you're beating them up for another 10% off. So beware.
Yeah. So I wanted to pick up on a couple of those threads. You mentioned up front, that if you don't have a specific supply agreement that specifies the quality of the cells you're getting, you can be guaranteed getting the worst cells that they produce.
That's right.
So
you're getting the dregs somebody else would touch.
So
when you
and understanding, absolutely. And so clearly it's also very important. You want to trust. Ideally, you like to trust, but you have to verify, right? And that's what the qualification and continuous sort of quality checking are about. But let's talk about the upfront agreement. What are the sorts of things, just so like in theory, you have some legal protection in the event that the quality starts to slip over time. What are the kinds of parameters that you want to set up in that type of supply agreement to ensure that you're at least supposed to be getting cells of adequate quality for your application?
I would often have binning that would hold them to a range. In this situation, we're making matched cell groups that we purchase from the manufacturer. And so we would have them bin to 0.25% of uniform capacity and 0.5% of uniform impedance. And they would provide us lots that met that matching, and they would also provide formation data. That's another really valuable thing you can get from your cell maker in your negotiations for buying is if you tell them, I need to know the formation data to know the voltage it left your facility at when it was packaged, then when you receive it and do open circuit voltage, you can know what your delta V was from the time that it left that factory until you received it. And if you see a drop in that voltage that is outside of the normal bounds, then you scrap that cell because it has high self-discharge and it'll eventually gas and fail.
And that's a great way to get visibility through like being able to organize all your data, because those formation data files, it's a lot, right? And to be able to track that.
You need a software like Tal's got to actually make useful decisions off formation data at a single cell screening level. Having a human try to screen thousands of cells from looking at plots is not practical for production.
I've done
works
it.
for yeah, we've
I've
all
done
done
it.
it, and it works for prototypes, but you really need to automate that with software to have a high volume production system working.
Indeed. And then when you do the incoming screening, did you advocate for screening every cell through if you have some automated means to do it? And if so, is it really just the OCV check and comparing that to what the final OCV of formation was, or is there another what do you recommend as just a high level screening program?
For every single cell, I like obviously OCV, and OCV is most valuable if you know that the voltage it was at before so that you can get a delta over time. But I also like a double pulse, which the beauty of the double pulse is it's manufacturing time practical, and that you can do 100 milliseconds at a given C rate and 100 millisecond rest and 100 millisecond discharge. And from that 10th hertz, you can derive an understanding. It's not going to tell you how the cell will perform, but it can tell you if you fall within the bounds that you're expecting. And this means that everything was wetted and that you had the right porosity of electrode, the right surface area of electrode, and that it's fully wetted as intended. This is something in theory that formation should always catch in a perfect world, but in practice, things escape formation and escape final QC, and that's why I love to do the OCV and double pulse for each and every cell that goes into the battery.
At a certain point in scaling, you need quality scientists, not just somebody who has a checklist, right, to go and make sure these things fit this. Like, you are chasing down these deep scientific issues.
And so that is what you would do for every cell that goes in the battery, but it's also important that you sacrifice, say, 10 randomly selected samples out of each pallet of cells that you do destructive testing with, so that you can understand that they haven't changed safety behavior. And
because they're not going to tell you if the electrolyte changed.
Right.
Or
when they change additives, you don't know. When they change, they can make changes that have very big effects on how the cell's safety performance behaves, and they don't say a word about it.
Yeah, and I think
it's very good to pull at least 10 from a lot. A pallet of cells might have 29,000 cells on it, and you pull 10, and those get fully abused to failure, so that you can benchmark where their safety margins are, so you know that what they're shipping you isn't any worse safety than what you validated.
Yeah, and
how does that? Yeah, please go ahead.
I like a few of the things that were key here. We're actually at like a magical time in the quality world today, where previously, historically, you only had samples to look at. You'd pull a sample off the electrode with a punch and measure that and get lots of data off that. With like modern analytics technology and modern imaging technology, you could actually get all of this data in one place. You could look at every cell. It is now possible to do that and not just do this off of samples, which is fantastic. These blind spots, talking about pulses, I love pulses. They're oftentimes a lot more reliable than EIS, which is very finicky from a lot of us who've used it in R&D context. You can do it well, but it's hard off every single cell.
Pulses are quick for production too. You can do it to every cell because it doesn't take 5 minutes to get your sweep. You can get your sweep in 2 seconds.
So we could spend a lot longer. There was another webinar series Kevin on our team just did with Novonix as well, just talking about all kinds of techniques. We could look at differential capacity and pulses and things like that. So if people those are on YouTube if people want to dig deeper, but a couple of quick pulses, you can model out not just DCIR, but you could also, if you record at high frequencies, also tease out what's going on in the battery cell and wetting and all that fun stuff. Encourage folks to dig in there if they want to get further. And then, I think there's a lot of questions just looking at the chat here on what are the blind spots people have? What are we missing? What are they skipping? And a lot of it, just this discussion, this data exists in formation. This data should exist in final OCV and initial OCV. And if you're not doing those things, do them. It may definitely measure your OCV of your cells, because that'll tell you if something has got a very different OCV, which means something's shorting in the battery. Don't put it into a battery pack. But then this data exists and people don't look at it very deeply. And so that's side one. Look at the data you have and then add as much metrology and analytics that you can to this. So add some pulses in there. T being bandied about as hammer that you could use on everything. It is expensive, even if you do it faster. So that's going to be more for sampling. And you can theoretically, we see companies starting to move towards doing that more. But there's a whole range of these techniques, and I'm interested from Erika and Luke, which are the new techniques you're really excited about that people are starting to add now into that tool set that you have to catch these quality issues?
CT's been a powerful asset, but it can also be misleading because your resolution of polymer materials, unless they happen to be ceramic coated polymer materials, you have almost no X-ray attenuation from them. And so you get just this ghostly haze of where your polymer materials are, even though you get very good resolving of where your conductive materials are. And I've unfortunately not been able to replace mechanical teardowns with CT alone until they can see polymer material better, which may be a physics limitation of X-ray attenuation.
We see some background in the chat here. Ultrasound could be a good complementary technique, and then sometimes you just do have to tear these things apart. Some exciting innovation on both CT and ultrasound that we're seeing in the industry.
I also, and again, I don't use this cell for production again afterwards, but as a destructive sample, I like to do the cryo-hypot too. I only started doing that about a year ago, but it's actually really valuable. Once your jelly roll is frozen hard, you can bring the voltage all the way up until the dielectrics break and hypot. And by benchmarking where this bounds is, it shows you what your tightest gap was, what your highest electrostatic field potential was, because you eventually bring it up until you break it. And so something you can sample from lot to lot, and it quickly tells you, is this separator full of holidays? Is my winding height correct? You can learn all those answers quite quickly from it. It doesn't tell you where your problem was until you unroll it afterwards and see where the arc part marks were in your hypot. But useful test. I enjoy it.
I would say as well, just something that comes to mind with cell qualification and testing and catching defects. And let's say you have this great process that you've gone through, right? You've done your due diligence with your supplier. You've established your line to be able to do that. You analyze it. There's still things that won't be caught, and you hope that's 1 in a billion, 1 in a trillion. And so battery pack design still needs to take into account the safety of the entire cell design, or just the entire pack, right? Trusting the cell suppliers, blaming the cell suppliers, like they have a really hard job and they do a phenomenal job, honestly. Like with the amount of defects that we see, especially on higher tier cells now, like it's truly incredible
how high the quality is.
Yeah, but you still need to design your battery to be able to handle, like, what if the worst case scenario? And I truly believe that we're in an age where great batteries can live 20, 30, 40 years even if they're designed correctly.
To take a question from Mike there, he says, can you comment on defect types that manifest due to environmental controls during assembly? I know of many recalls that happened because of humidity control failures. If your anode side has humidity problems, it doesn't particularly matter. It'll be fixed in your vacuum bakeout series. But if your cathode side has humidity environmental controls, you'll form hydroxyl groups that after it's wetted will make those cells puff and self-discharge and fail. And basically any cells that are made while the humidity isn't adequately low will have to be thrown away. Those are hazardous. Question from Greg on passivation.
I don't know how we're doing on time, Tal and Eli.
We're fine.
Okay.
Question from Greg about passivation with thionyl cells. Sorry that I can't help you with thionyl cells. I've never had a job where I worked with them.
Yeah, I'd love to pick up on where Erika was starting to go with this. Again, one of the topics that we promised our audience to cover today was how cell level issues influence battery pack quality and manufacturability. And so ultimately, most of the time, we're taking these individual cells, we're building them into modules, pack systems to deliver more power, more energy, and do big and important things out in the world. So I'd love to turn the discussion to how do these things you recommend looking for a sort of a tight distribution of OCV and impedance and things like that. So when those things get out of whack, when you start assembling packs and systems from cells that aren't properly matched, what are the things that are likely to manifest? I know we have a pretty technical audience, but I'm sure there's some folks out there that
one major concern in a battery pack is if you have impedance mismatch in the same parallel group, it's a positive feedback loop to make that situation worse. And what I mean by that is, let's just say in the most simplest system, we have two cells and one is a little higher impedance and one's a little lower impedance. Then every time we pull from these groups, the cell that's lower impedance will have the bulk of the current share from any demand that we place on the system, which will mean that it gets warmer. And as a result of getting warmer, its impedance will go down lower, and this mismatch will further exacerbate. So it's a positive feedback loop to track premature failure from that system due to asymmetrical active material use. The lowest impedance cell ends up getting its butt kicked. Every time you're regenning and every time you're on the throttle, that cell is asymmetrically carrying the burden. And this is why even a pack will last much longer, even if all the cells are a little higher impedance, if they're similar impedance in those parallel groups to each other.
I have another viewpoint of that question too, where let's say you're mixing lots, right, from the same supplier or something like that. The reason why we recommend safety testing so much is because if those little additive changes, let's say you have the joules of energy release, it could be significantly different, even if you have the same amp hour cell. And so if you're designing your battery pack to be able to withstand a certain amount of joules of energy release, and then it's totally changed, like that completely can change your design. And
Yep. Cell makers don't like to talk about the electrolyte changes they make for either performance improvement or cost down, but the electrolyte changes they make can have such huge changes on the safety behavior. Even
usually
the
for the
temperature
better.
it initiates, often it is for the better, but not always, which is the scary thing. We see some changes that make better electrical performance out of the cells, but they'll initiate thermal runaway, say 10 to 15 degrees sooner. And this is one of the large aspects of what determines when TR occurs is actually stability of SEI. And the stability of SEI is related to what the additive package they decomposed in preformation and formation to grow those layers. And the cell maker changes this package without telling anyone. And this changes the onset of thermal runaway initiation behavior as that initiates from SEI decomposition generally.
Awesome. Tal, I wonder if you had any thoughts or observations on what we've seen in industry regarding screening at the pack level once these things are assembled. Is it at that point too late to catch these sorts of mismatch issues, or what kind of techniques exist, and what's the likelihood that some of these things can be caught further downstream than just the cell level?
Yeah, I think this comes back to just one of the comments Erika made. It's like a lot of folks, especially if you get to later stages in the production process, you're moving away from the electrochemists and the engineers who understand fundamentally what's going on. And so it was some sort of spec, they're checking a box, and that data is there, but people don't look at it very deeply. Those imbalances across the pack, it's within spec, it's fine, but like it's one of those insidious things. That imbalance starts compounding over time, and then all of a sudden, a couple of years later, you have an issue in the field, especially when you're putting many cells together in a large battery pack for a vehicle or going on the grid. And the trade-offs actually are really hard. It was interesting. I know, at Electric Goddess, you work both with like companies who are starting to build up these programs in the development phase, which is your favorite, and then the other side is on the back end. Once something has gone wrong, how do you fix it? And it was a conversation with a startup within the last week here, and they're building their first like large utility system, and they can't build as many cells as they'd like, how close to their tolerances need to be. And they're going to have imbalances in those early systems, but they need to get a demonstration out there. And it would be interesting from your perspective. How do you deal with that at the early stages? Is it just something that you want that system for demonstration, shift it out as soon as you can? How do you look at figuring out what those tolerances should be in a production system?
Early stages for me, as sad as it sounds, involve numbering each cell, then doing electrical screening on each cell, then forming a spreadsheet where you show what is a standard distribution of your good cells and where to draw bounds for outlier conditions. Yeah. And it's not easy and it's not fast. And when you're doing it the first time, it's a lot of manual setups, the way that I do it, at least. You guys probably have your tools to do it than I do.
Indeed. So there's a related question from the audience from Shankar. Is there a separate standard or tolerance level for either impedance or capacity for packs for EV versus stationary energy storage applications?
Okay. Where it matters to be fussy with impedance is how tight your design can maintain parallel cell group temperature matching. Because let's say that you match them all to 1/10 of 1% impedance, but you put it in a design where one side of this cell group is 5 degrees warmer than the other side, then it doesn't matter that you matched the impedance. They're going to be off by 20-30%, even if you started with perfectly bent cells. And that comes down to good cells don't necessarily mean a successful battery. To have the successful battery, you also have to meet the conditions needed for the cells to share current and to live in the wild together. So for ESS systems, getting uniform temperatures is much easier because you're often in a climate controlled environment, or at least in a stationary situation. And whenever you're building a stationary situation, it's so much easier to achieve temperature uniformity because things like weight and size are less precious than in automotive. People underestimate even the effects of solar gain, but when you park your car, pull your car into the sun, and the sun rises in the morning or whatever, and one side heats before the other side, and now we've measured temp degree deltas as big as 10 degrees across battery packs that weren't being used, that were just sitting.
I think I would also say with BSS is that they're usually at much higher voltages than EV batteries. And so when I just glaze through pinhole defects, I would really look into that on the system level, because no matter how tight you get your cells, the system being at that voltage just increases complexity and likelihood of
the types
issues.
The types of things you can get away with in a lower voltage pack is not to say you can be sloppy and have it work, but compared to ESS strings at 1400 volts or so, there's no margin. Even a single stranded wire that all the strands didn't tuck into the bundle and it has one strand poking up at 1400 volts, you have the electrostatic stress potential, if that's a sharp tip on the wire, to actually break the air down, ionizing into an O2 into O radicals that form ozone and then degrade all the plastics and dielectrics around that site. And all you did was have one strand of wire poking up in your battery pack, and now your polymers degrade because they're full of radical O species.
So sometimes it is the cell's fault, but a lot of times I think a lot of those things are overlooked, especially when using higher quality cells. I did also see something on Second Life pack building on our
Please.
channel.
Yeah, I'd love to hear what you have to say on that. That one caught my eye as well.
There's
Comments on
no
building
way
Second Life packs. Yeah.
There's no way I could even address it here, Eli, because we have an 1.5-hour video where we literally just talk about the nuances of it. And the summary of it is that it's extremely risky to us. So unless you have something that is like a super cool tester, and in that, if you do have, I want to talk to you because I'm super excited about that. But I haven't necessarily seen, there's a lot of opportunity there to make me comfortable with Second Life.
Yeah, one of the big scary challenges with Second Life is we've helped folks go through this a bit, and you can have a module that electrically tests great. The impedance and capacity is nominal, and you say, all right, we got a good one. And then you open that module and it might have surface corrosion all over the cells, or processes occurring haven't yet failed, but are failure, or even electrolyte weepage and leakage. And the module tested great. And this is one of the big scary challenges of Second Life is my capacity and impedance isn't the big gatekeeper for if I can use this Second Life module. It's more about nuances in isolation detection to try to screen for corrosion or ionic pathways. And people focus on the electrical testing so hard with Second Life, and it's like that's actually your easiest of all the tests for Second Life is capacity and impedance. That's like the gimme easy test to validate, but that's not the test that tells you it's safe to pile a warehouse full of these. That test requires knowing that they're not a fire hazard, and you can be a fire hazard while having nominal electrical performance.
Yeah. Was it an accident? Was there any cracks in the insulation? Was there all these things that are subtle and hard to tell, especially when these things have been often bounced around in their first application? Those mechanical things and corrosion often end up leading to those issues. So it's really hard, and I think it's going to be even harder in the near term just because of how quickly costs are dropping for cells. We're seeing this economies of scale kick in. You can get a new cell with a warranty that was substantially cheaper And then when you factor in all the like logistics and testing and both that needs to be done to recertify a cell, essentially, pack or system, it's a really tough balance. So we encourage people to work on it, but our caution is probably better to just use new cells and new systems at this stage.
Yeah,
And then
Yeah.
also recycling.
I feel like it's something that we were hearing a lot more about, say, 10 years ago, when people were starting to think, oh, there's going to be all these batteries coming out of vehicles, and they'll only hold 75% of their initial charge. We got to do something with them. But the fact is, and we've covered this in webinars before, is that just a baseline technology improves by a couple percent every year. So by the time you have a battery that's 8 or 10 years old, whatever's replacing it is already substantially better, 50% or more better performance around cross capacity, energy, power, all those things. And so the goalpost just keeps receding for those second life batteries, and then compounded by the potential safety risks. I think Erika was being diplomatic in saying that there's room to make her more comfortable. I think we would.
I've sifted through enough ashes that my
Yeah.
level of paranoia is very high.
Yeah,
And we're doing
editorial. Yeah, please.
podcast on this
Sorry,
too.
you
If you
cut
want to
off
get
me
it very in depth, we made a 90-minute podcast just answering this one question that's on our website. So.
Yeah.
Sorry,
Excellent.
Eli, what were you saying?
I was just saying, I think all of us on this webinar and everybody in the audience, we're all very interested in helping to advance and expand and grow the battery industry, and building large packs and systems out of second life batteries. I think our concern is generally that it's going to lead to safety risks that could hurt people and property, and ultimately damage the prospects of the battery powered future that we're all here to build towards.
I get why people want to do it. Like, recycling is super gnarly at the end of the day. Like, it's so metal. And I get it. It starts with still manufacturing the best battery pack you can, right? Because the longer you let it live in that first life, you don't have to spend a lot of money like testing it, and you're going to have to add all new wires, putting in a new system. Like, the best battery operates in the system it was intended to operate in, right? So if you're taking car batteries and then putting them into stationary storage, it's not optimized for stationary storage, but it is a cool representation of like how you could repurpose them if you
There's
overcame a lot of things.
Factor too, Eli mentioned a little bit, but that when you're choosing between buying a new cell today or using second life cells, many of the new cells today, their cyclic stability is so much better. Your total round trip energy ROI on new cells, if they can buy you, if it's the difference between 1,500 cycles and 8,000 cycles, that new cell suddenly is the lowest ROI, total round trip energy cost and everything, over using second life. Simply because cell chemistries and electrolytes and additives have improved enough that many cells have windows you can cycle energy through them, not the entire SOC range, but windows you can cycle energy in them where they do so little degradation per cycle, it's challenging even to measure it.
Yeah, and just a little plug, if people do want to dig in, one of the big challenges with recycling batteries, if you're not going to put them in a second life application, is just neutralizing those battery cells and then transporting them safely. And Erika and Luke have a startup, Redivivis, that has some pretty cool technology that folks should check out as well.
Thanks.
Thank
Appreciate
you.
it, Tal.
We cryo-freeze, blast, shred, and neutralize. And you can shred the batteries when they're cryo-frozen with no sparks or fire, and you don't even smell anything because the vapor pressure of the electrolyte as a solid is so low that it's a very clean process.
It's again one of those problems people don't even realize. Just think they could pick up the batteries and discharge them and good to go, or just shred them right away, and you'll end up with some gnarly fires again on that side.
We learned that the hard way when we thought we were going to receive low capacity functional packs, and we were like, we're all set up to discharge. Turns out, I don't know if we've ever received a functional battery for battery recycling yet. If they still work in their low capacity, somebody just uses it till it stops working, and then it comes to the recycler.
Mm-hmm.
Vinci asked about pinhole detection strategies.
I like
things that would not get caught in the initial characterization.
I like to use holiday detection brushes, which is where, and it depends on the geometry of the system you're trying to look for pinholes in. But let's say that if you have a tube-shaped part you're looking for pinholes in, say cooling, powder coating, or whatever, then you slide a brush over that is a round wire that has these little metallic brush prongs coming off of it, like a little wire brush bristles. And with high voltage, you have potential that you slide it across this material. And if it arcs, if it's able to pass that high voltage to your base conductor, then you know that you have a pinhole defect. And if you're doing a flat surface, then use a wide flat holiday detection brush. And you can simply drag it across the surface in 1 second. Or obviously there's automated holiday detection too. If you have a line, then every time you have the surface pinhole sensitive, you drag it into the holiday brush. And if it breaks out, then you know you have a pinhole defect. But it can trying to find them with your eye or with a microscope is basically not practical.
So you wouldn't
And,
see those in electrical characterization, those pinhole defects?
If the pinhole's on the inside of the cell, you can see it as additional self-discharge. But if the pinhole is on an outside surface or a dielectric or a bus bar or a coolant tube or a cold plate, any of those systems, you've got a pinhole defect with holiday detection. And holiday detection is really good. You can find sub-micron pinholes that are smaller than a wavelength of light to even be able to see them optically, and yet you pass the brush over it, and if there's a defect, it arcs to the brush, and you pull that part or rework it depending on what the application is.
Fascinating. So I know we're getting towards the end of our hour, and I want to give an opportunity for Erika and Luke. So again, you've mentioned a couple things that I'm sure the audience would be really interested in. You talked about a podcast series. You talked about your recycling company, Redavivus. So are there any resources online or otherwise, podcast series you'd like to point our audience toward to learn more about some of this stuff? Again, Second Life sounds like you've got some content out there about that. So where can the audience find you and find out more about the things you've been talking about today?
Thanks. You can go to electricgoddess.co to reach our website, where we have a bunch about our services. We have our videos up on there. I saw a question of how often for extensive level testing, and something I've seen through many different projects is it's definitely a lot easier, quicker, and cheaper to hire people like us or whoever that is, whoever you get along with the best, early in your process. So if you are doing anything with batteries, setting up those systems and knowing which direction to go in a world where they tell you so much, it's definitely great to connect early. And so we offer a complimentary 30-minute call to just talk about what your project is and see if there's alignment there. And I just hope to talk to many of you. I can't even see everyone. Just hello to everyone.
Also, I would add, when you're starting a new program, it's way less expensive to start out overkill on QC and screening, and then dial it back as production runs and you build trust with your cell maker and your manufacturing processes. But the most expensive way you can possibly introduce a product with a battery is the way where you have to recall and destroy them all, right? And people often think these warranty replacements are so expensive when a pack fails and I have to give them a replacement battery. But that's actually your lowest cost option that happens when you send bad batteries. You can, unfortunately, in math, say you're selling electric bicycles or electric skateboards or something, you can sell 10,000 of them that are good, and one quality defect slips and it burns a house down. And that was the margin for the other 9,999. And this kind of math doesn't, and again, it may lead to having to recall the whole other 9,999 as well, depending on if you can understand what caused that fire or whether it's a risk to property again. Yeah, definitely the lowest cost way you sleep best at night and your company's best success is overkill QC starting out.
Yeah,
and then
analyze your
maybe
data.
you have space to remove some of the extra paranoid QC checks as you go, but you don't want to go in the reverse order of learning that you should have QC'd harder and now you have to go recall all the products and buy all the new houses and structures that burned down because of it.
Indeed. And just briefly, I'm going to tell the audience that if you would like to connect with Electric Goddess or connect with Voltaic to see a demo or talk about your battery program and how we might help in the analytics side, there's a pop-up on the screen that'll point you in that direction. And then I'd love to turn it over to Tal, if you have any final thoughts, comments on this. I know as we were talking about sort of the costs of not finding defects, these are some things you think a lot about, talk a lot about with people in industry. Any final thoughts from you?
Yeah, and I think for both our organizations, both Electric Goddess and Voltaic, we're often dealing with this on the back end when companies have literally spent many millions of dollars trying to correct these things in their products. And it's just getting those products out the door. It is so much cheaper to spend a little bit of time making sure you get the design right, building in the data systems. They could all be automated. This could all be happening. We are in a golden age of quality. But yeah, on the back end, whether it was trips to India, and there's a lot of excitement there, but some folks are just rolling out batteries, and we hear about like 20% of the batteries having issues, service issues. But that goes across energy storage systems where the big Chinese and Korean suppliers have to send people out to sites and go replace modules and racks, and vehicles that are bad packs not making into customers' hands. Like spending your time up front is actually going to save you time down the road to really get the cost here. Even when it seems like these programs are going well, the back end costs that are absorbed by the business in terms of warranty returns and all of the physical work and cost it takes to go send people out to sites is incredibly expensive, and not to mention the recalls, the safety issues. But I think, ending note here is just engage with us, help us work with you on the design side with Electric Goddess, on the voltaic side, let us help set you up with those digital systems that'll help you get set up going forward in the future here. And the SDI recall maybe is a good reminder of that. Even the best here still struggle.
No one's ever made a perfect cell. Just you find cells that have acceptable levels of defect to not impact your application negatively.
Excellent. I think that's a great note to finish on. So again, thanks to everyone who joined us for the past hour. Thanks to Tal Sholklapper from Voltaic, and of course, Erika Guerrero and Luke Workman from Electric Goddess for sharing their expertise. And please follow up and check out their content online, connect with them. And it's been great spending the last hour with you. We look forward to seeing you again online or in person. And thanks again to the audience. It's been a great hour. Thanks, everybody.
Thank you.
Thank you for the opportunity. It's always great to see you guys. And when you go to battery shows, you guys should know Voltaic throws the best parties at all the battery shows. We're grateful.
Thanks, man.
See you.